We got into chapter 3, which is bonding. And we talked about
about
kind of
kind
the
of the
overall a couple of types of bonding that we'll talk about, which is we have ionic bonding.
bonding.
And ionic bonding is always between a metal and a non-metal. And as we talked about with those periodic trends, the metals really do have all the properties that want them to sort of release their electrons or give away their electrons, while the non-metals pretty much have all the properties of they would like to accept them. So what we end up getting in this situation, because of that, is a transfer of electrons from the metal to the non-metal. Again, that's going to result in our cation formation and our anion formation. And once again, it is these opposites attract that hold that together. A reminder again, in an ionic bond, as we talked about, there is no sharing of electrons. And it is that sort of opposite attraction that holds that bond together. We also talked about covalent bonding, and it is a little bit different. It is, again, between kind of two nonmetals. Because it is between two nonmetals, that essentially does mean that they have very similar periodic sort of trends, which essentially means like most nonmetals, they want to hang on to their electrons. They actually want to kind of collect some more electrons. So again, the result of that is the best that they will do is some type of sharing, as we'll talk about today. And again, that sharing, as we will see, will be equal or unequal type of sharing, but there is some aspect of sharing that's going on. We also saw in terms of ionic bonding, and in general, we could use Lewis dot symbols, or just sometimes called electron dot symbols. And that is basically the symbol one dot to represent the valence electrons, as the valence electrons are the only ones involved in bonding. And we could use that to show something like ionic bonding, like we saw, for example, I think we did lithium and fluorine. And again, in this situation, a little 1s2, 2s1, 1s2, 2s2, 2p5 in this case. Lithium is going to send over its electron. Remember, at that point, it will become positively charged. Our fluorine will pick up that electron, become negatively charged. And what's going to happen is, one second here.
All right, so hopefully that's better. I'm just getting like feedback and hearing myself. I don't want to do that. All right, so as that happens, again, the lithium does become positively charged. The fluorine becomes negatively charged. The result of that is really the basis of all bonding. Our lithium will lose its one valence electron and become 1s2, or the same electron configuration as helium. The fluorine will pop that electron right there into the p subshell and fill it up at that point, and we'll end up at neon's configuration. And again, as we talked about, that is essentially the whole point of all bonding, is for everybody to achieve noble gas configuration, or again, end up basically in the same sort of electron arrangement as the noble gases, as they're very, very stable. Any questions on that? As we also saw towards the end there, when we're talking about, say, calcium and fluorine, in some cases it's necessary for extra elements to sort of be involved. Like, for example, in that example we did, we do need 2 fluorines to basically take an electron each, as they can only accept 1 each. But calcium does need to lose 2 electrons again to get to that noble gas configuration. And again, as we talked about at the end, that is why when we write an ionic compounds formula, we always want the charge to equal 0 between the positive and negative guys in the simplest way possible. And the real basis of that, again, is the bonding aspect of it. It allows everybody to achieve noble gas configuration and be sort of happy. Any questions on any of that there? All right, then we're going to continue on with the next type of bonding, which is covalent bonding. And again, a reminder that covalent bonding is pretty much our two nonmetals together, which is going to be our sharing of electrons. So Gilbert Lewis suggested the role of electrons in bonding, hence why we call them Lewis structures and stuff like that. Our dots and stuff are out of the way here in the wrong spot, so I'll just redraw this. So we have, say, a hydrogen and a hydrogen coming together. In this case, clearly because they're the same element, for example, they have definitely the same periodic trends. So neither one of them is going to want to give up its electrons. So what's going to happen in this situation is instead of getting a transfer of electrons like we do in ionic compounds or ionic bonds, we're actually going to get sharing of electrons. And those electrons will be shared between the two hydrogens in this particular case. And what that means is the two electrons there will go for the guy on the left. They will also go for the guy on the right in this case. And this is the formation of a covalent bond. You could also show it like it's supposed to look down here with a line. One line represents the sharing of two electrons. So one line is two electrons. Two lines, which is a double bond, is the sharing of 4 electrons, and 3 lines is a triple bond, as we'll talk about, is the sharing of 6 electrons. This is important because, again, they're not going to sort of give away their electrons and accept their electrons. There's not going to really be a transfer of electrons. But by this aspect of sharing electrons here, the hydrogen on the left there has 2 electrons, and the hydrogen on the right will essentially have 2 electrons. And that's good if you again look at the periodic table in terms of those locations, as we talked about. And as a good reminder, hydrogen should never have more than 2 electrons. And again, that's because it just needs to get to helium to basically achieve that noble gas configuration. And by sharing of electrons here, they're able to do it. So the major difference between, say, a covalent bond and an ionic bond is that sharing aspect of it. In a ionic bond, we have a transfer of electrons, which allows everybody to kind of achieve that noble gas configuration. In a covalent bond, we kind of achieve it through sharing of electrons between the two atoms in a particular bond. Any questions on that there? So covalent bond is sharing, and it is that sort of mutual attraction that kind of holds that bond together. So if you think about something like hydrogen, there's going to be sort of those electrons attracted to the positive nucleus of the hydrogen on one side, but also attracted to the positive nucleus of the hydrogen on the other side. So that kind of mutual attraction on either side sort of locks the electrons in and allows them to basically make that bond. So if we take a look at an example of something like fluorine, and we look at the electron configuration for fluorine, 1s2, 2s2, 2p5, we do have 7 valence electrons for fluorine. And again, in this situation, what's going to happen is because they are both, again, fluorine, we're going to get this sharing of electrons that is going to occur between the two, and it's going to result in a bond forming between them. Again, we have no transferring of electrons in this case. You can represent, again, the bond part of it with dots between the two atoms. I will say that most people will represent sort of the bond part of the picture with a line. I personally do, but it's not incorrect to use dots on that side as well. And again, in this situation, we got the sharing of electrons. And as you can see here, fluorine on the left has 8 electrons, and fluorine on the right here will end up with 8 electrons. Again, as we talked about, 8 is that sort of magical number in terms of bonding. It is the same number of valence electrons that group 8 has, which is our noble gases. So again here, through sharing those electrons between them, each of the fluorines are able to sort of achieve that stable configuration, just like the noble gases. Any questions on that there? Yeah. There are no charges on these at this point. Remember that when you have an element that is by itself, it has no charge. It only gets a charge when it's really, we only really get charges, full charges, when a metal and a non-metal come together is when we get full charges, like full positive and negative charges. In covalent bonding, we don't get full positive negative charges. There is a type of covalent bond that we'll talk about in just a second that does have partial type charges to form. But in this particular case, because they're both the same elements, we would actually expect the electrons here to be shared equally between the two and stuff like that. So it would be sort of a neutral sort of bond. Other questions on that? So when we do look at these electrons, there are different types of electrons which are present in this particular molecule. All the ones that are represented here as dots, these are what are referred to as lone pairs. They're also more commonly nowadays in books referred to as non-bonding electrons. I personally will probably call them lone pairs a lot of times, but if I say lone pairs, non-bonding electrons, it's basically the same thing. I think nowadays most books, like I said, kind of roll with non-bonding electrons rather than the lone pairs. We also have another type of electrons, which is obviously the electrons that are in the middle, which are being shared and making that bond. And they obviously have a special name known as bonding electrons. Very creative there. So our bonding electrons are the electrons that are being shared within a bond. Non-bonding electrons are the dots on the outside. Whenever you draw these type of Lewis structures like this, especially for really any Lewis structures, especially for covalent bonding, you should make sure that you do show both of those types of electrons, the non-bonding electrons and the bonding electrons. We personally use dots here for non-bonding electrons. Don't use lines. We're not in organic, so sometimes organic they use lines for non-bonding electrons. So use the dots for non-bonding electrons here in this class. So a Lewis structure is again a representation of covalent bonding. It is showing basically what is happening with those electrons. And again, in the case of covalent bonding, we have some sharing of electrons happening again, rather than a transfer of electrons. A reminder again that it is only the valence electrons which are shown in the Lewis structure or Lewis symbols. Remember, they still have a lot more electrons present, those core electrons, but it is only the valence electrons which are involved basically in bonding. So take a look at another example like water, which is H2O. Again, here, oxygen started with 6 valence electrons. Hydrogen has 1. So when we look at water here, there's a number of sharing of electrons sort of occurring. So here, the hydrogen and the oxygen on one side is sharing electrons. That's going to allow the hydrogen to get to 2 electrons. The hydrogen on the other side doing the same thing, going to allow it to get to 2 electrons. And the oxygen, through sharing with both of the hydrogens, will now be able to achieve 8 electrons and again basically be stable and reach that sort of noble gas configuration. And again, as I mentioned previously, that is essentially really the purpose of all bonding, is to achieve that noble gas configuration. So the two magic numbers, in a sense, in terms of bonding, is 8 and 2. And we'll talk about situations where maybe we go over, but the one place where we never go over in terms of electrons is hydrogen. Never, ever, I'll say it one more time, ever more than 2 electrons. So if you find yourself in terms of hydrogen, drawing things and putting dots, you should also just put a line because it's going to be wrong. If you triple bonded and then put dots, you should probably put 2 X's because that's super wrong. Yeah, so don't do any of those things. Basically, hydrogen will always just pretty much look like this in a structure. One line which represents 2 electrons, and that's all it should have. Everybody else, again, you should try to, in most cases, shoot for 8. And like I said, we'll talk a little bit later on in the chapter where perhaps we might go over 8 in certain situations. All right. That brings us to those 2 rules there. The octet rule is the rule that says basically everybody will continue to make bonds until they have 8 valence electrons around them. Again, just going to allow them to get to that noble gas configuration. The one exception is, again, hydrogen. As we just talked about, that's sometimes referred to as a duet rule. Again, because really hydrogen just needs to get to helium to sort of be stable and like a noble gas. Everybody else past helium pretty much needs to get to 8 to get to the last column there. And that's, again, why everybody else will pretty much need 8. So let's talk a little bit about multiple bonds, which we sort of touched upon a second ago. We have, for example, here a single bond. And once again, a single bond is represented by 1 line. And again, that 1 line represents the sharing of 2 electrons. So like fluorine that we saw. And sometimes that is all you need to get to the octet rule. You don't need more than single bonds, and everybody will be sort of happy in that situation. But there are certain situations where single bonds will not cut it, and you do need perhaps a double bond or more than 1 double bond to sort of achieve the octet rule. And for example, carbon dioxide here is an example of that. The carbon is actually double bonding with the oxygen on each side. And the result of that is, as we can see here, it's going to allow everybody to basically reach the octet rule. It's going to give the oxygen on the outside 8, going to give the oxygen on the other side 8. And once again, it's going to give the carbon in the middle there also 8. And again, in this case, it's necessary to actually, for carbon, in this case, to double bond on both sides to also get to those 8 electrons. So again, sometimes it does require double bonds. And again, a double bond is 2 lines and basically means that you are sharing 4 total electrons or 2 pairs of electrons in this particular case. Now, again, in another situation, maybe double bonds will not cut it and it will not get you to the octet rule. And at that point, it may require a triple bond happening. And that's the case here, for example, in nitrogen, our C2H2 molecule here. So a triple bond is going to be 3 lines. Again, the sharing of 6 total electrons are 3 pairs of electrons to do that. So as we get into drawing Lewis structures for covalent bonding and covalent molecules, a very common, I would say perhaps error that a lot of people make is they kind of want to double bond or triple bond like right out of the box as they're drawing these sort of structures. It is best, I would say, in most cases, to not really double bond or triple bond right out of the box when you're drawing these type of structures. You should try single bonding first. If that doesn't work, you should kind of roll to double bond. If that doesn't work, then you should roll to triple bond. And that usually will give you a pretty good picture when you're all said and done. But kind of double bonding, triple bonding out of the box is not really the best approach. And we're going to talk about how to draw them properly in a bit here. All right. So when we talk about covalent bonding and we talk about sharing of electrons, how do we know if the electrons are going to be shared equally or unequally? The major sort of determining factor in terms of whether or not electrons will be shared equally is really electronegativity. So as we talked about in the last chapter, and we'll see here again, really the definition of electronegativity is the ability of an atom to bring electrons towards itself. And as we talked about there, when we talk about periodic trends, electronegativity increases as you go up and to the right, decreases as you go down, with fluorine being the most electronegative element you could have. And it really is when we're talking about kind of between two elements, really the thing that you want to look at in terms of how these electrons are going to be shared equally or unequally is that electronegativity. So electronegativity helps us sort of define and distinguish between covalent bonds. So for example, if we took our hydrogen example that we saw earlier, when we look at the electrons that are being shared between the two hydrogens, the idea here is since they are actually both hydrogen, they're going to have pretty much the exact same electronegativity sort of value, which means they both are going to be pulling those electrons towards themselves equally, kind of like tug of war, right? It's the opposite ends of a rope. Everybody pulls equally, right? It's a little flag in the middle, kind of just stays there, it doesn't go anywhere, right? And essentially you got kind of equal sharing of electrons. So in a case like H2, or even a case like the F2 that we saw earlier as well, we also have two of the same elements. We would expect, once again, those electrons in the middle to be pulled pretty equally on either side. And that's going to result in equal sharing of electrons. And basically what that means is it's kind of like a neutral bond. It's just like kind of pulling the electrons equally in each case. Electrons are not going to be closer to one side of the bond than the other. We're going to have pretty equal distribution of the electrons across that bond. And that is what is sometimes referred to as a nonpolar covalent bond. Or most people just roll with the nonpolar bond, as nonpolar would imply a nonpolar covalent, and it is a covalent bond. So a nonpolar bond is a bond where you get equal sharing of electrons. Electrons are not sitting one side in the bond more than the other. And the result of that is you can kind of think of it as kind of like a neutral bond. There is, again, no like positive side, no negative side. It's basically nice and equal distribution of those negatively charged electrons. Now, if we were to, for example, take away one of the hydrogens or fluorines, depending on which one we're looking at there, and put them together, we now have a bond where we do not have the same elements. We still have sharing of electrons there between them. But in terms of electronegativity, as we just saw there and we talked about, in terms of electronegativity, the highest electronegative atom is, our element is fluorine, which means between hydrogen and fluorine, fluorine is going to go, I would like the electrons a lot more than you. And what's going to result in this case is those electrons, because of the high electronegativity of fluorine, will actually end up, if all these terribly drawn green lines represent the electron density, all the electrons mostly will be hanging out at the fluorine side. A little bit of it will still stay over there at the hydrogen side. And what we're going to get in this case is unequal sharing of electrons. And unequal sharing of electrons is what is known as a polar covalent bond, or just a polar bond by most people. Now, there is sort of a consequence of these electrons in this type of bond not being shared equally. And the idea is this, that we can represent this type of bonding, by the way, with an arrow. And this is what is sometimes referred to as a dipole arrow. And the type of arrow always points to the more negative side of the bond. And this back part here that makes like a plus sign is the more positive side of the bond. And that is because if the electrons are hanging out closer to the fluorine should be more positive or more negative? Should be more negative, right? Electrons are negative. So if you have them all hanging out there by the fluorine, It will actually become more negative. And it will actually create a partial negative charge on the fluorine. And because the electrons are moving away from the hydrogen, it will create a partial positive charge on the hydrogen. Those are delta negatives and delta positive symbols, is what those little squiggly things are. And we will get this charge separation. So the difference between a nonpolar bond and a polar bond is, in a polar covalent bond, you have this unequal sharing of electrons, which means electrons are hanging out on one side of the bond more than it is on the other side. And that's going to create a negative charge on the side where the electrons are hanging out, and a more positive charge on the side where they're moving away from. And that's different than a nonpolar bond where you have equal sort of sharing of those electrons. Again, it's kind of like a neutral bond. There is no positive side, there is no negative side. It's just kind of like neutral, no charge happening, because the electrons, again, are basically being distributed equally across that bond. Question on that there. By the way, why is it a partial positive charge and a partial negative charge, and not a full positive charge and a full negative charge in this situation? What's that? Yeah, so we have only partial positive charges and partial negative charges because the electrons are still being shared here. They haven't fully transferred from one element to the next. And because there's some aspect of sharing here, it is only a partial positive and a partial negative charge. That's different than when we talk about something like sodium and chlorine. That sodium is going to send the electron completely over to the chlorine, and that's going to create a full positive charge on the sodium and a full negative charge on the chlorine. And that's what creates the ionic bond, because we get the complete transfer of electrons. In a polar bond, because they are still hanging on, so it's kind of like the tug of war sort of example. You got somebody pulling really strong on one side, and the poor guy is like barely hanging on and moving into the mud pit as they kind of pull the rope, and he's hanging on with like 2 fingers, but he's still hanging on, being dragged on the ground. But these electrons are still being shared in this case. And that's why, again, they're partially positive and partially negative. So any questions on that difference there? Okay. And obviously it's an ionic bond. I figured I wrote over this. So reset. All right, so as I talked about just there, and we just talked about, again, something like a HF bond, we will have some differences in the sharing, and they will be unequal sharing, which is our polar covalent bond. And again, it really is that difference in electronegativity which helps us determine what type of bond it's going to be. Is it going to be nonpolar? Is it going to be covalent and polar, our polar bond versus a nonpolar bond? And again, it creates those sort of partial positive and partial negative charges that occur as a result of the unequal sharing of electrons. Again, that this mirrors the electron density, a lot more negative on this side, a lot more positive on this side. And once again, we could represent that with that arrow, which is very commonly drawn. Again, pointing to the more negative side, backside to the more positive side of the bond in this case. So when we think about the different types of bonding that we've talked about, there is some slight differences of what's going on, or some major differences, I guess, of what's going on when we look at it. So when we look at sort of the 3 types of bonding that we've talked about up until this point, on one end of the extreme, we have really like an ionic bond. And once again, that is going to be our metal and non-metal. And once again, here we're going to get that transfer of electrons as we just talked about. That's going to result in our cation and anion formation. And once again, that is what's going to be holding that together. No sharing of electrons. An example like sodium chloride that I just used there a second ago. On sort of the other end of the extreme, we have a nonpolar bond. And it is covalent. And it's between 2 nonmetals. And we have equal sharing of electrons, like F2, H2, and those sort of examples. And sort of in the middle of the two is we have our polar bond, which is also, again, covalent. And that also is between two nonmetals. The difference here is we're going to have unequal sharing of electrons. And an example would be right there. And again, that's going to create our partially positive, partially negative charges, which also, again, can be represented by that. So at one end of the extreme, nonpolar bond covalent, nice equal sharing of electrons. On the other end of the extreme, definitely no equal sharing of electrons, just going to get that transfer of electrons because the nonmetal is going to grab them from the metal, basically, and the metal is going to give them up. And in the middle, we don't have equal sharing of electrons, and we don't have such unequal sharing that it gets transferred, but we have unequal sharing of electrons where both parties are still hanging on to the rope, if you will, are the electrons, but definitely one of the parties are kind of pulling the electrons closer to themselves than the other. Any questions on the three different types of bonding here? And then clearly anything involving two nonmetals is going to have some sharing of electrons pretty much. And anything with the metal, nonmetal, because of those periodic trends, we're going to see that transfer of electrons happening. Any questions on that? So as I mentioned before, and really, I'll put it this way, more specifically, electronegativity is really the thing that we look at to determine whether or not we have a nonpolar or polar covalent bond. And we could also use it to look at ionic bond, but as we'll talk about here in just a second, you really don't need electronegativity to determine if it's an ionic bond. As you look back at sort of what I just did a second ago, when we look at the ionic bond versus our two different covalent bonds, the major difference that we see is in an ionic bond, it's a metal and a nonmetal, right? Both of the covalent bonds are nonmetals together, which means, frankly, although people will use electronegativity sort of values to help them determine perhaps ionic bonding, you really don't need it. It pretty much, if you see a metal and a nonmetal together, move on with your life. It will be ionic. Yeah, and pretty much you'll be in good shape of that. So really, electronegativity is a lot of times used to focus in on covalent bonding where we have sharing of electrons between nonmetals. And again, as we talked about, it is the ability to bring electrons or attract electrons towards itself is what electronegativity is. It is related to electron affinity and ionization energy that we talked about in the last chapter. Again, electron affinity is the energy change that occurs when somebody gains an electron. And that's usually what we talk about when we talk about anions. And ionization energy is the energy required to remove an electron from an atom. Fluorine, for example, has high electron affinity and high ionization energy, and it will also have very high electronegativity. It has high electron affinity, which means it likes to gain electrons, and it has high ionization energy, which means it does not like to give away electrons. It likes to hang on to them, and it's going to also want to attract electrons towards itself. Sodium, on the other hand, which is on the other side of the periodic table, has low electron affinity. It's really not looking to gain electrons, and it has low ionization energy, which means it's very easy to remove electrons. So it's more apt to give away its electrons in that situation, and it has a low electronegativity. So when we talk about electronegativity and helping us decide between polar and nonpolar bonds, a guy by the name of Pauling, who did a lot of work in a lot of things, also came up with one of the first ideas of DNA. What it looked like, it wasn't correct, but he came up with it. He also was big in like vitamin C, like megadosing vitamin C. Pauling came up with a sort of scale for electronegativity, and the Pauling scale runs from basically 0 to 4, and 4 is the most electronegative, and 0 not so much. So pretty much not electronegative there, a value of 0 pretty much. And we can use what is sometimes referred to as the change in electronegativity. So delta is the change in electronegativity values. And if you take the two elements that are involved in a bond and you basically subtract their electronegativity values, and you get anywhere from 0 to 0.4 difference, that is considered a nonpolar bond or a nonpolar covalent bond, right? If you do the difference in electronegativity and you basically just take the two values and subtract them, by the way, you just take the two values and subtract them. So you get a positive number, larger number minus smaller number. And you get above 0.4, which is, I guess, 0.5, to below 2. That is some type of polar bond, unequal sharing of electrons, also covalent. In general, if you're above 2, that would be some type of ionic bond. No sharing of electrons. And again, this is what I was talking about a second ago. Although you can use electronegativity values and subtract the 2, and if you get over 2, it's an ionic bond. You don't really need to. Again, if you see metal, non-metal, it's ionic. You don't actually need the values to help you determine that. I will also say that there are some combinations between a metal and a non-metal in terms of electronegativity values that will give you actually less than 2, but it's still an ionic bond. So it's best for ionic bond. You don't really need to kind of use the electronegativity values. You just need to use that's a metal, that's a non-metal. We're going to have an ionic bond is going to happen. So let's take a look at this. So here is a electronegativity table, and as we've talked about, as we go up and to the right, we do see an increase in electronegativity and a decrease as you go down. As you can see, fluorine is 4 there, which is the highest value in the upper right corner. We do not see noble gases on this chart because noble gases they're happy the way they are, right? They're chemically inert. They're not going to really react. They're not looking to do much. Everybody's trying to be like them. So if you ever needed an electronegativity value for noble gases, most people use 0 for those. So they're not really looking to do much in terms of electrons attracting them or anything like that. So to show you how to use a table like this, which obviously would be provided for you, or the numbers would be provided for you if you needed them. Let's take our 3 sort of examples, or a couple of the examples that we saw before. We have sodium chloride. We did HF, and we had F2, right? If we just look at them. So for example here, if we wanted to calculate the difference in electronegativity values, we'll look up sodium. Sodium is 0.9. Chlorine there is 3. So we would calculate the difference in electronegativity. Again, just basically subtracting larger number from smaller. That gives us a 2.1. Remember that anything typically 2 and above is going to be ionic. And this would tell us that this is an ionic bond. As I mentioned before, you really don't need it because that is a metal and a non-metal, and that should tell you. But for example, if you took something, say like sodium and bromine, for example, and you put them together, sodium is 0.9, bromine is 2.8, so the difference would be 1.9, but it's still ionic and it's less than 2. So for the ionic sort of aspect of using electronegativity, it's not perfect number of 2, it's in the ballpark of 2. So again, as I mentioned, non-metal, metal is pretty much all you need. If we go to our fluorine and our hydrogen is 2.1, our fluorine is 4, and we do the difference in electronegativity here. That's going to give us 4 minus 2.1. I believe that's a 1.9, if I'm not mistaken. 1.9 falls between like 0.5 and 2. And that's going to mean that it is going to be a polar bond because of that, where we should have the arrow pointing to the more electronegative atom, which is the fluorine in this case, and creating that sort of bond. Again, we would have, in this case, as we just talked about, a more partial negative charge on the fluorine, more partially positive on the hydrogen. Now, if we go to our fluorine and fluorine, that's a 4 and a 4, which means the difference in electronegativity would be 4 minus 4, which is 0. That is definitely between 0 and 0.4. That is a nonpolar bond, which means we have equal sharing of electrons. If you get actually a difference of 0 in electronegativity values, it is a nonpolar bond, but sometimes books and people will classify it a little bit differently. They sometimes will classify it as a pure covalent bond. It is still nonpolar, it's still equal sharing of electrons, but it's kind of like as perfect equal sharing as you could get. Obviously, 0.4 is considered still equal sharing, but in reality, it's slightly not equal, right? There's a little bit of sharing unequally happening there. But if you hit a perfect 0 there difference, it's going to be a pure covalent bond, which is still a nonpolar bond. Again, the perfect sort of sharing of electrons. Any questions on that there? All right, why don't you try a couple of these combinations here? Let's see. Let's say you had a bond between, let's do carbon and oxygen, carbon and hydrogen. Let's do sulfur and oxygen. We'll do carbon and sulfur. And let's do potassium and fluorine. All right, for each of these bonds, is it ionic? Is it polar? Is it nonpolar? And for anyone that is polar, draw your dipole arrow in the correct. Okay, so let's take a look here and see. We'll start with the K and F. So we have sort of a bond between those two. Looking at K and F. F is 4. K is 0.8. So that's going to be a difference in electronegativity. I believe there of 4 minus, whoops, 4 minus 0.8. 3.2 without the calculator, we'll go with that. That's definitely above 2. That's going to be ionic. Again, we really don't need it because we do know hopefully that potassium is a metal and fluorine is a non-metal, which again, it should be an ionic bond just based off of that. We look at carbon and oxygen. Oxygen there is 3.5 and carbon is 2.5. Which means if we take the difference in electronegativity, 3.5 minus 2.5, and go with 1. 1 is above 0.4 and below 2, so that should be a polar bond in this case. Arrow should head in which direction? Arrow should head towards the more electronegative, which is the oxygen in this case. The oxygen would be more partially negative than the carbon, which would be more partially positive in this case. Question on that one. If we look at carbon and hydrogen, carbon is 2.4 and or 2.5. And hydrogen is 2.1. Change in electronegativity, 2.5 minus 2.1 is 0.4. That is the upper end of nonpolar. And really, this bond is the reason why that is. And that's because pretty much all organic molecules are carbons and hydrogens, and they're nonpolar. So the carbon-hydrogen bond is considered a nonpolar bond. This is what I was talking about also. The difference is 0.4, which means are these electrons being shared perfectly equal? The answer is no, right? They're hedging a little bit towards the carbon in this case, but it's not considered enough to be unequal sharing of electrons, so it is still considered a nonpolar bond. Because it's a nonpolar bond and there's technically equal sharing of electrons, you do not draw a dipole arrow because there is no side that's more positive or it's negative. It's more neutral in this case. Yeah. Yeah, so in this case, we're just looking for really the difference. So we don't want a negative sort of number because you always take the larger minus the smaller. Yeah, so we get a positive number. Other questions? All right, we did carbon, hydrogen. Let's do sulfur and oxygen. So sulfur is 2.5. Oxygen there is our 3.5. So if we do our difference in electronegativity, that's 3.5 minus 2.5, which is 1. That definitely is above 0.4, below 2. So this is going to be a polar bond as well. In this particular case, we would be heading the arrow towards the oxygen, which should be more negative in that bond as it's more electronegative and bringing the electrons closer to itself versus sulfur. Lastly, here we have carbon and sulfur. So carbon is 2.5 and sulfur is 2.5. So the change in electronegativity is 2.5 minus 2.5, which is 0, which means that this bond here is actually a nonpolar bond. And this brings up a really good point. For sure, if you have a bond between the same element, it's going to be nonpolar because they're going to share equally. It is possible to have two different elements that actually share the same electronegativity. Why might that happen? It's actually based on their location on the periodic table. We look at the location between carbon and sulfur. They are, as we like to say, diagonal of each other. Yeah. So although one is further up, one is a little bit further to the right, and they cancel out their differences. There's a few places that occurs. You can see nitrogen and chlorine as well, diagonal of each other. So they're not usually straight diagonal. They're kind of diagonal and over one, and that gives them the difference that it is. So there are a couple of places diagonally on the periodic table, for example, that end up with the same electronegativity values because of that diagonal sort of relationship. So you do have to be careful that I would say probably in 9 times out of 10, if you have two different elements that are non-metals, you're probably going to end up with a polar bond. But there are some places, as you see, you can end up with a non-polar bond based on it. Now, do you always need the table and the numbers to make a pretty educated guess? The answer is not always. You probably in 97% of the time, 95% of the time, could probably make a pretty logical and probably correct guess in terms of electronegativity and how the electrons are going to be shared by using just the general trend in electronegativity. If you are comparing two things, for example, like we did here between carbon and oxygen are right here. They are in the same row on the periodic table, and oxygen is further to the right on that row. And we know things further to the right are more electronegative. So just knowing the places of those two things in the same row, it's going to be a polar bond. There's going to be enough of a difference. You don't really need the numbers. So if you're comparing something that's in the same row, probably the guy further to the right should be obviously more electronegative, and that will usually create a polar bond. Also, if you look at something like we did here between sulfur and oxygen, they are actually in the same group on the periodic table. And what we know in the group, as you go up, it is more electronegative. So here we would know, based on the placement of those two, that oxygen should be more electronegative than the sulfur. You don't really even need the numbers. You can make a pretty educated guess that it's going to create a polar bond. So in general, if you're comparing two things in the same row, our group on the periodic table, you don't need the numbers. If they are off from each other, which they would be, then most likely will create a polar bond. And you can make a pretty educated guess on that. Any questions on that? Once again, what we are talking about here, just so that we're clear, is what is sometimes referred to as bond polarity. And that really is, in most cases, what you would use electronegativity for is to determine whether or not between those two atoms, that particular bond is polar or nonpolar. It does not, as we will talk about all the time, especially when you have 3 or more atoms involved in a molecule, tell you if the actual molecule is polar or nonpolar. So that is what is referred to as molecular polarity. The entire molecule as a whole, taking into account all the bonds that are present, is that molecule going to be polar or nonpolar? Bond polarity is typically what we use electronegativity for, specifically between these two guys, these two atoms in a bond. How are they going to share the electrons? It may not always be the same as the molecular polarity of a molecule, as we'll talk about. The only place where bond polarity, what we just did, and molecular polarity will be the same is when you have a diatomic molecule. So if you have a diatomic molecule, which basically means there is only 2 atoms, and we could just use the 2 that we looked at here already. We could use like F2 and HF, for example. And obviously we have just did our electronegativity values and differences. And I believe this guy obviously has a difference in electronegativity of 0 and making it a non-polar bond. And here our difference in electronegativity, I believe, was 1.9, which made it a polar bond. So the bond polarity here is we have a non-polar bond on the left and a polar bond on the right. And these type of molecules here, which are diatomic, are the only ones where bond polarity and molecular polarity are for sure the same. And that is because when we look at this guy right here, how many bonds does this molecule have? It only has 1 bond. And because this molecule only has 1 bond and that bond happens to be nonpolar, that would mean that this molecule is going to be a nonpolar molecule. And that would be the molecular polarity for this molecule because its one and only bond is nonpolar, so it has to be a nonpolar molecule. Same thing over here when we look at the HF, it has only 1 bond, which is this guy, and we already determined that that bond is polar, which means since that's the only bond in the entire molecule, this would also has to be a polar molecule. So only with diatomic molecules do you find that bond polarity and molecular polarity are the same, are always the same. When you get to 3 or more atoms and you have a lot more bonds happening in a molecule, you have to look at some other things, which we'll talk about in the next chapter, but you have to actually look at other aspects of the molecule to determine the molecular polarity. But if you're dealing with strictly a diatomic molecule, because it only contains 1 bond, if that bond is polar, the molecule will be polar. If that bond is nonpolar, it will be a nonpolar bond. That is why, for example, when we did the little experiment there with the halogens, and it was like Cl2, Br2, and I2, all those are nonpolar bonds. And they're all diatomic molecules, which is why they were all nonpolar molecules. And that is why they were really great with hexane, which is also nonpolar. So that's how we knew those things were nonpolar. Question on that there. We will talk officially about molecular polarity when we get into the next chapter. But just since we have this here, this molecule, which is polar, we can draw that bond dipole. In the case of this, if we're talking about molecular polarity, this arrow is also sometimes referred to as a dipole moment. And polar molecules will have a dipole moment, and it means the same thing. It means that on that side where the arrow is pointing, the electrons are sort of crowding around and becoming more negative, and the other side is becoming more positive. Nonpolar molecules do not have dipole moments because they share the electrons overall in the molecule equally. All right. All right, so that's sort of our scale there that we talked about. not too many people use sort of the bottom part all that much these days, but sometimes bonds are characterized by percent ionic character. So if you have 100% ionic character, you pretty much have an ionic bond. And if you got like 0%, you got a nonpolar bond. And any percentage in between would be more of a polar bond that happens. Most people talk about it as being polar, nonpolar, or ionic. Not a lot of people these days use percent ionic character. Here's that pure covalent that I was talking about before. It is still a nonpolar bond, but again, that's like the perfect equal sharing of electrons that you're going to have. So as we saw there, atoms with widely different electronegativities, we got something on the left-hand side of the periodic table and the right-hand side of the periodic table, they will have a pretty big difference in electronegativities. And that is why typically when we put a metal and non-metal together, we get that ionic bond that forms. When we put two non-metals together, which are crowded in the same spot on the periodic table, they also will have very similar electronegativity values, which will not give you a big difference between them. And a lot of times will result in some type of covalent bond that's going to happen and sharing either being equally or unequally. And obviously our two general sort of things to think about just in the big picture of bonding, metal, non-metal, definitely ionic, two non-metals going to be sharing and covalently bonded together. All right. That's what we talked about there. All right. All right, so then let's talk about Lewis structures for really covalent bonds and covalent molecules and sharing of electrons. So we're going to talk about the steps to draw Lewis structures, and you should follow these steps along the way. It will give you a pretty good picture when it's all said and done. So the first thing that you want to think about when you're going to draw a Lewis structure is how is this molecule going to be sort of arranged? How are all the atoms going to be sort of arranged? Who's going to be bonded to who? I would say in most cases, if you have like one element and like three of a different element, the one element is probably in the middle and everything else is attached to it. But to help you decide, in general, the least electronegative atom should be in the center. So the least electronegative atom should be in the center. And in a lot of cases, everything is going to be probably bonded to it. There could be more than one central atom, but in a lot of cases that we deal with, you'll have kind of one central atom, but it is possible to have more than one. With that being said, we should never put hydrogen in the middle, because if you put hydrogen in the middle, it's going to have more than that dreaded 2 electrons, and it's going to get you an X. Yes, so don't put it in the middle because it will have more than 2 electrons. We should also never really have fluorine in the middle because it is the most electronegative element you could have. So it shouldn't be in the middle. They should be on the outside. Probably the most important thing when you're drawing a Lewis structure for a covalent molecule or molecular molecule is really the second thing here. You want to count up the total number of valence electrons in the molecule. Remember that the number of valence electrons equals the group number on the periodic table. So you want to count up all the number of electrons that are available to you for your picture. You also want to keep in mind that if you come across something that's an ion, like a polyatomic ion that has a charge, you do need to adjust your electron count. Otherwise, you'll be off in terms of your picture. So again, things that have a positive charge means that it has lost electrons. So you need to subtract off that charge from your total. And things that are negatively charged have gained electrons. So you need to add that to your total. The reason this is most important is when you are done with your picture, you got to have exactly that number of electrons in there. You can't have more, you can't have less. You got to hit that number on the nose. We also should think about electrons as not belonging to a particular element. And that is where some people go really wrong when they start drawing Lewis structures is they go like, well, they do what I like to call piecework. Like oxygen's got 6, nitrogen's got 5, and he's got to like move electrons here and there. And what usually happens when people try to do kind of piecework drawing is they end up with too little electrons, too many electrons, not the right bonds and stuff like that. So what we want to think about is when we get this number in the second step is we want to kind of equally distribute these electrons to all the elements that are there in this particular compound and kind of put them out there equally. Not that this guy needs 3 more to get to 8 or this guy needs 2 more to get to 8 or whatever it may be. And that's usually where people kind of go really wrong. Once you have the logical arrangement, and if it is something, I think, by the way, that you might not know the logical arrangement, I would probably tell you how it's connected. But in most cases, it's probably pretty logical as to figure out how it is. What you want to do is go from the single, you want to go from the central atom to each of the outside atoms. And all you want to do here is a single covalent bond. So for me, I use lines, but if you want to use dots, you can, but I'm going to use lines for that bond. Again, here, we're not going to double bond or triple bond out of the box. We're going to do a single bond to everything on the outside. Once you do that, each single bond would count for 2 electrons. You have used up some of your electrons from your total. You'll have some electrons left over at this point. Each of those leftover electrons goes on the outside atoms first in pairs of electrons. And you want to fill up all the outside atoms with those electrons until everybody on the outside hits the octet rule with 8, unless, of course, it is hydrogen, right? Then no dots around it, right? Now, if you filled up all the outside atoms and you still have electrons to go, then you go to the center atom, the guy in the middle, and you put them on as pairs of electrons to the center guy. At that point, once you're putting electrons on the central atom, you should be out of electrons at that point. This is where you want to check to make sure that everybody has met the octet rule, except for hydrogen, which should have 2. And it is at this point that if you find everybody has met the octet rule, you've distributed all your electrons, you probably have the correct structure sitting in front of you. Now, if you look at somebody and they're short, like they don't have 8 electrons, it is at this point that you try to fix that. And the way that you fix it is by making a double bond and see if that works. And if a double bond doesn't work, then you need to make a triple bond. So here we do want to save kind of double bond and triple bond action for any type of situation where somebody has not reached octet rule and to try to fix it at that point. Again, you don't want to double bond or triple bond out of the box. Any questions on that part there? So let's go through one together just to see how it works here. Let's do NF3. So the first thing I'm going to do is count up the total number of valence electrons. Nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which gives me 26 valence electrons. So in my picture, 26 valence electrons is what I should have. Logical arrangement, bless you. When I look at nitrogen and fluorine, they are in the same group, and we know fluorine is the most electronegative atom, so it cannot be in the middle. So logical arrangement would be nitrogen in the middle and fluorine going to be attached to it. So again, here I'm not drawing any bonds, I'm just getting them in the logical arrangement. You could put, if you wanted to, the fluorine up on top or bottom. It doesn't matter where you put that kind of third fluorine. You could go up or down. It really doesn't matter. Now that I have the correct arrangement, I got my electrons. Here we go. Time to start bonding. I'm going to go from the single bond from the center to each of the outside ones. Just a single bond. And each of those single bonds represent 2 electrons. So that is 2, 4, 6, 8. Who we appreciate? No, it's only 6. We'll go with 6 there. And that is 20 electrons still left to go. So these 20 electrons are going to go on the outside atom first in pairs. So we're going to go 2, 4, 6. That is now filled because it's got 2 on the other side to make 8. 8, 10, 12, that is now filled because again, it's got the Y on the other side that makes 8. 14, 16, 18. So at this point here, we have put onto our picture 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 total electrons. So we put 18 more on there. We still have 2 electrons we need to put on our picture. Everything on the outside is filled. we go to the center and we line it down again in pairs of dots on the center. And now we have placed all 26 electrons at this point. We want to make sure, lastly, here that everybody has met the octet rule. So once again, 2, 4, 6, 8 for that guy. 2, 4, 6, 8 for that guy. 2, 4, 6, 8 for that guy. And if we look at our nitrogen, 2, 4, 6, and 8. Everybody has 8 electrons without all the highlighting. That would be your proper Lewis structure. And those are the procedures that you should follow so that you do end up hopefully with the right picture along the way. Any questions on that there? All right, so why don't you try one here? Why don't you do NO3 minus? Draw the proper Lewis structure for that one. See what you come up with. Okay, so let's take a look and see. So we're going to do the same thing. We're going to get our valence electrons. And here we have 5 for nitrogen. Oxygen, there are 3 of them. And oxygen is group 6, so there would be 6. Now there is a negative charge. Add, subtract, what do I do with it? Negative means it has gained an electron, so we do need to add 1 more to it, right? Again, if it was a positive charge, it means it has lost it, right? So you would subtract it. So again, you want to make sure you're not short or have too many electrons in your particular picture in this case. So that's 18, 19, 24 electrons in this case. Again, 24 is the important number as that is where we need to end up. So in this case, nitrogen and oxygen, once again, if you don't even have the values with you, they are in the same row. And we see nitrogen is further to the right there when we look on the periodic table, which means oxygen is probably going to be more electronegative. Also, in most cases, like I said before, you got 1 nitrogen, 3 oxygens. Probably that one guy is going to be in the middle. Everybody's going to be attached to it. So nitrogen in the middle, some oxygens around. We're going to do our, again, single bond here to each of the outside atoms. That's going to use 2, 4, 6 electrons. So if we subtract 6 off of that, that leaves us like 18, I think, left. We're going to go on the outside here in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 at this point. We have now filled up everybody with all the electrons. Is everybody good in this case? No, nitrogen is short, right? So nitrogen has 2, 4, and 6 electrons. Everybody else has 8. All the oxygens there, 2, 4, 6, and 8, and they're all the same all around. So in this case, this is a point where everybody did not meet the octet rule. I try to erase that and not the picture. Let's see here. There we go. So we do need to make a try to fix it here. Can I just put a couple electrons there? I cannot because now I have 26 electrons, which is too many. So this is the part where we're going to try to make a double bond to fix it. Doesn't matter which oxygen I choose in this case. It really doesn't because they're all equivalent. They're all exactly the same. So you can lay up a double bond wherever you want. Can I just draw the double bond in like so? I cannot for the same reason. I now have 26 electrons as well. In addition, the oxygen up on top now has 2, 4, 6, 8, 10 electrons. Too many electrons. So when we make a double bond and also when we go to make like a triple bond, if necessary, what we are actually need to do is actually we need to take a pair of electrons and we're going to bring that pair of electrons in to make like the double bond. And when we do that, we will end up with a picture where we have now double bonded up on top. And we could also single bond this away. And for good measure, since it is something with a charge, we typically put brackets around it with the charge on the outside. Now, when we look and we start to count up electrons for everybody, oxygen up on top, 2, 4, 6, 8. Oxygen to the right, 2, 4, 6, 8. One to the left, 2, 4, 6, 8. And our nitrogen now with the double bond, 2, 4, 6, and 8 there. So everybody has now met the octet rule. We still have, if you count up all the electrons, we still only have a total of 24 electrons, which is exactly what we should have. Now, as I mentioned before, first off, any question on that? As I mentioned before, you could have double bonded to the right if you chose to, and it would have been perfectly fine. So your picture would have looked something like this. And you could have double bonded to the left as well. And your picture would have looked something like this. All three of these pictures, either one of them, one of the three would have been correct. They are also related to each other. These are what are known as resonance structures. And resonance structures are, as we can see here, oftentimes arise when you have more than one option where you could make, for example, a double bond. And the reason it happens is because each one of these pictures are correct in an aspect, but the double bonded electrons in this particular case are sometimes referred to as being delocalized, which means in certain times of the day, they're over there at that oxygen, but they could be at that oxygen. They could be over at the oxygen on the right. So they're sort of moving around. So they're probably a combination. The true structure is a combination of between all three of those pictures. So any one of those could be drawn. And a resonance structure typically will have these little arrows between the pictures to indicate that they are resonance structures of each other. So if you were asked to draw a Lewis structure for NO3 minus, you could have laid up any one of the three pictures. If you're asked to draw all the resonance structures for it, you should draw all three of the structures. Yeah. Any question? And really, the simplest way to think about it is just wherever you have the option to kind of move the double bond, you could draw another Lewis structure that's equivalent to it. Any questions on that there? All right. We'll stop there, I think, for now.